All right, so let's start here with the single electron model and see how it works. Electron, sorry. So much of what happens in condensed matter physics and in solid state physics, which are the same thing, right, is with a very simple Hamiltonian. So we have a very, very simple problem, and that is that we want to solve, and this is the Hamiltonian for this, a summation over states of the momentum operator squared over 2 times the mass of either an electron or a nuclei, whatever you're using for your approximation, and the potential that this electron feels. And in this case, it's a summation with two electrons here, L and L prime. And then you have these two vectors here as actually the position operator in this case. So we have a sum. This sum is ranging over all the electrons and nuclei in a solid. We also have that ml is either the mass of an electron or of a nuclei. So let's say you had you have a massive system, and this m is just the mass of it, and then this L tells you whether you have the L label tells you whether you're an electron or a nuclei that you're summing over. And then the Q of L is the electronic charge of that electron or that nuclei, where L again is the same label. And then there's 1/2 in front of it. So let me pick in somebody. Let's see, I see a hand up. Solfidin, yes?
Okay, I am so sorry. Before you start, do you uh, did you think about commenting on the tiny machine that you wanted us to watch?
Oh, not yet. We'll save it for next class when we're all in person.
Oh, I see.
Okay?
Okay. Thank you.
Yeah, anything else?
Thank you.
All right. So let me see if I have a volunteer. Anybody? Or if I have to pick a volunteer. Why do we have a 1/2 in front?
As far as I remember, this was because if we do a sum over all the particles, could be electron, could be nuclei, then we do sort of a double of that. It's an overcompensation because we take into account the interaction between, let's say, particle 1, particle 3, but then there would be another term which would be for particle 3 and particle 1.
Mm-hmm.
So it's the same thing, but it's being doubled. So we have to put that half in front of that.
Exactly. So that's the reason that you have the 1/2. You could rewrite it that you go with L has to be greater or equal to L prime or something like that, right? So anyways, this is a really simple equation, but if you wanted to solve it when all the electrons and nuclei are interacting, you have that you can do it maybe for 10, 20 particles on a supercomputer. So very simple, but only 10 to 20 particles can be solved this way in a supercomputer. And how many particles do you have in an actual solid? Well, you will need to get a computer if you wanted to calculate a chunk of material that can solve about 10 to the 23 particles. So that's a big, big number discrepancy, right? So how do we deal with that? Well, you actually have to do a series of approximations. And each of these approximations, they're not particularly well controlled. It's just because we have to find a way to solve it. So it's a really hard problem to solve, and they have to find a way to solve all of this. So one approach is to replace this original equation with simpler ones. Some of the replacing that we're doing cannot be justified all the time. But what you want to do, even if you cannot justify this, is that you want to capture some of the essential features of the systems. So this is the art of electronic structure calculations. And it's a really difficult problem to solve, again, but people have been doing it for maybe 80 years already, maybe more. And some drastic simplifications make it so that now you can solve some equations analytically. Most of them are done numerically, except for very simple models. And the simplest of this is called the free Fermi gas simplification. So everybody here knows who Fermi is, right? Who doesn't know who Fermi is?
Like, I don't know all about him, but I heard him.
Okay, so he's the last physicist that was a great experimentalist and a great theorist. Although there's a story that he almost blew up Chicago once. I don't know if you guys know that he was involved in the chain reaction.
The first cyclotron sort of thing.
No, actually, it was whether you would get a chain reaction if you put enough nuclear material together. So he miscalculated, and then the pile of nuclear material started to get super hot.
Oh no, that one I haven't heard. That's a news. That's a news story.
He was in Soldier Field, so he might have, if he had taken coffee breaks longer, maybe Soldier Field explodes and half of Chicago goes with it.
But wasn't he involved with the atomic bomb project? The project?
Yeah, exactly. For that particular project, he was doing those kind of experiments, figuring out whether you would get a chain reaction if you put enough fissile material together. And you do.
Oh,
yeah.
So the cyclotron thing was before that. Yeah.
Yeah. But in this case, the reason that it's a Fermi gas is because it's about fermions, right? But before doing that, let me tell you before getting into all of that, let me tell you about what this model tells us. The first thing is that we're going to turn off Coulomb interactions. So we're going to have particles, and the Coulomb interactions between electrons and electrons and electrons and nuclei and nuclei are turned off. Now then, the other thing that you're going to do is that you're going to consider the electrons moving freely around a box. Giant box, right? And that's where the free part comes out. And the last thing that we're going to consider is that this is the only non-trivial thing, right? Because if you have 10 to the 23 particles, but they don't interact with each other, and you just have to solve for one. The only thing that is non-trivial is that the particles obey Pauli's exclusion principle. Now, this is where I get to ask, everybody's familiar with Pauli's exclusion principle or not? Speak up if you're not.
I'm not aware.
All right, so I'll get into that then. So for instance, if we have this model, we can apply it to metals. And in fact, for metals, some of the metals are reproduced very well with this free Fermi gas. And it's interesting, right? Because you're just considering this part of the Hamiltonian, not the other collection of parts. So some metals work really well.
So, sorry, so the other part would be the one with the 1/2 would be the Coulomb interaction.
Right.
That is the fourth. Okay, yeah.
Yeah. In fact, if you're looking at something like sodium, this free Fermi gas, and in fact, all of the alkali metals, so not just sodium, but the whole row of the first row on the periodic table, first column of the periodic table, all of those are alkali metals. And the free Fermi gas model captures some of their features really well. All right, so when does it break down? If you have a system that is an insulator or a magnet, then this free Fermi gas is not gonna be able to, there's nothing that you can do to this model that allows you to get the behavior of a solid that is an insulator or a magnet. So that tells you that insulators and magnetic interactions are probably very related to this side of the equation, right?
Excuse me, I have one question.
Yeah.
What does this ton of Coulomb interactions means? It means just because we are considering single electron as well, or we are ignoring the positive charges?
We're gonna ignore that second term completely. We're just gonna have a collection of particles that are there and have a particular charge, but then that charge term of the interaction is not considered when solving their motion or anything. You just consider the kinetic energy term.
Okay,
Okay?
got it. Thank you.
Mm-hmm. All right, so let me then start with this. So Pauli principle. The Pauli principle is the main thing that that comes into play here. And to get to that, let's start with the following. Let's assume that we have mainly you have a crystal, and then how do I erase all of this? All right, so the thing that we're considering sorry about that. I thought I knew how to use this. All right, it doesn't matter. Let's do it again. All right, so this is not a classical system because we're assuming that the electrons, the wave nature of the electrons is important. The other thing is that what we have is that the electron is a fermion. And because the electron is a fermion, it has to be limited by the Pauli exclusion principle. The Pauli exclusion principle tells you that only one electron can occupy one given state. So that's the way that it works for fermions. That's what electrons are. For bosons, there's no such restriction. And then the other thing that it's just from last time, this is the wave function. And this thing right here is the charge density, or if it's the wave function of an electron, right? Well, it would be the particle density. If we square it, the wave function, and what we have here is if it's the wave function of an electron, it would be the electron density. So this Pauli exclusion principle and the behavior of waves, in this case, the wave function, which tells you how much electron density is in a space, are the important things to have. And remember, we're talking about electrons, so it has a particular charge. So let's do it.
Sorry, if I can ask quickly.
Yeah.
So by electron density, you mean the probability of an electron being there?
Yeah.
Okay, thank you.
All right, so let's start with the following as an example, right? What I'm talking about is sodium. And then if you remember sodium, where does sodium belong in the periodic table? Zachary?
It's the alkali metals. I think I don't actually know the periodic number, but it's pretty high, or pretty low. But it's, I'm sorry. Where else did you want to know about the periodic table? Can you hear me?
Dr. Barunda, I'm not sure if anyone else can hear you. I can hardly hear it. It sounds like your microphone is muted, or maybe you set your notebook over the microphone.
Oh.
That's better.
All right. So,
Yep.
All right. So yeah, Zachary, you got it right. It was that alkali. So what happens is that if we have a nuclei in black, then an electron, this is just a classical figure, right? Is there. And if we had just one more electron, we would have lithium. But in this case, you don't have more than that. But basically, sodium and all of the guys, lithium, sodium, and all of the guys in that first row of the periodic table, they all have what is the valence electron. So this guys is called the valence electron, is the outermost shell of it. And then all of those guys are the core electrons. Okay, so we can say that sodium behaves, and all of the guys in that first row behave as if their valence electron was the only one interacting with each other, and all of the other electrons are tucked into the core. So lithium, sodium was below sodium. Anybody?
Oh, what was the question again? Sorry.
What's below sodium?
Rubidium.
Periodic table?
Potassium, I think. Potassium.
Ka,
Okay.
potassium.
After sodium,
Okay.
in the same column, it's potassium. So 11 and then 19. Yeah.
Yep. All right. So all of those guys behave almost the same way. So now the other thing that happens is that we had a potential, a radial potential, and we could say that this is the potential that the electrons are feeling. So a way to think about it is that, let's say that we had a crystal, and the crystal is huge, right? In this crystal, we're going to make it so that the electrons cannot be outside of this box, but it's a huge box. And here, the boundary of the thing goes up to infinity, so it's like a particle in the box system. But you also are going to have that there's this potential there. And this potential from the ions interacting with the system or the electrons is basically something that goes like this. Okay? And then you actually have that the ions behave like all of them. Each of these guys would correspond to having the core of electrons and the ions of the system. And you would have something that looks like this. But the idea then in this Fermi gas interpretation is that this potential, this is the Coulomb potentials, Coulomb interaction, Coulomb potential right here. And then this one is the crystal H, right? So everything is bounded to be inside the crystal. What we're seeing in the free Fermi gas simplification is that this Coulomb potential is way smaller than the bound of the system. So this is basically just a tiny little perturbation of the system that does almost nothing.
Dr. Brenda, can I ask a quick question?
Your electrons. Yeah, go ahead.
Sorry to interrupt. So is this like what we explained yesterday with the potential well and these vertical lines that you're drawing? Are these supposed to be the potentials within that well, or I guess I'm having a hard time understanding this illustration. What are these red vertical lines that you've drawn?
Yeah, that would be, so you have, we're thinking of, in this case, a sodium atom, right?
Right.
And this sodium atom, or whichever one that is in the first row, all of those guys are represented by these guys here.
Okay.
So those would be the positions of the atoms, and they would have a potential that is like this. That's the Coulomb potential.
Okay, so these marks that you drew here, these red ones with the Coulomb potential, that's just the graphical expression of
that
Coulomb. Okay, sorry, I just wanted to make sure I was tracking.
Yeah, but then the approximation, what it's telling you is that we're doing is that these potentials from these guys is so tiny that we're just gonna, compare to this size of the crystal, that we're just gonna assume that it doesn't exist.
Okay.
Okay. So now what we have to solve is the same problem that we talked about last time, which is just the particle in the box, right? And we said that the particle in the box was just gonna be, and then we had that it has eigenlevels. And this Hamiltonian term right here multiplying the wave function is the same as if you multiply this wave function by just some numbers that we can find. So this is the Hamiltonian, the E of n are the eigenlevels, and in this case is the energy of the system. All right, let me turn on my light because it got dark. So the ions are there, but they barely contribute. It's kind of like little bumps, and it's a periodic potential because the position of the sodium or whatever ions on our crystal is periodic, right? So this is a periodic potential that is little tiny bumps compared to everything else, so we can ignore it, this ion core. So once we do that, we're just looking at the particle in the box, and then we know that there's a boundary condition here. So let's assume that this crystal, oh, now it's erasing. So this is 0, and this right here is L, right? So now, because it's a crystal and our electrons are waves because they're quantum particles, you have to obey that boundary condition. The potential goes to 0 at the boundary. So that means that our electron waves all have to have and obey that there's 0 here and 0 here. So that means that there's a particular wavelength for the electrons. Is that clear? If not, tell me.
Actually, I
Dr.
have a
Brenda.
question.
Yeah, go ahead.
You can go ahead. I think someone was asking a question.
Oh, I was just gonna say, just a little note. Whenever you say here and here, sometimes we don't see the mouse actually move.
Oh, okay.
I think I understood what you were talking about, but
All right, so let me color it. So your electron has to be 0 here and has to be 0 here. So your electron wave, right? So that means that this electron wave has a wavelength that is given by this value, the wavelength right here. Okay? And that means that we also know, given this.
And I'm so sorry. I wanted to ask something too before you continue.
Mm-hmm.
So this Coulomb potential lines that you've drawn inside this O and L crystal bound, they are represented with this VR formula that you wrote, which is Z divided by 4P ER.
Mm-hmm.
Okay, so these positions from O to L, this position change, where is that represented as variable inside this VR equation that you have?
I'm sorry, which one?
So the O and L crystal bound
Uh-huh.
positions of these Coulomb potentials, where they correspond to this equation, you have VR equal to.
Oh no, so the CR would be centered on each of the. So there's a potential coming out from here, right? And it's centered on each of the ions. But the
I see. Each of them is VR. I see.
Each of them has this particular potential that we're talking about centered around them. And then you have to add them all together. All right, but we're ignoring it, right? And then we know that it's a particle in a well, that it has a particle in a box that goes from 0 to L. So that means that we already know the solution to this one. And we know that the energy levels are given by this thing right here. There's no potential, that's just the energy term. And that we can talk about how to solve it, but you guys have done it. I think it's not h bar, it's just h squared over 8ml squared. And this is where you just find out that the boundary conditions tells you sine, is cosine, and so forth. And in fact, we can talk about this just being the energy of the first eigenstate multiplied by the value n squared. You have another question? No? All right.
No, I
Yeah,
had this
sorry.
before, but you didn't say, so I did ask my question.
Okay.
Yeah, I do have a question. So you said this energy En corresponds to n squared E1, and that's an approximation, I presume.
No, this is actually the particle in the box solution. Our approximation is that the whole crystal with the 10 to the 23 atoms inside of it, where there's 10 to the 23 potentials that we have to worry about, is actually gone, and we just have a particle in the box.
Okay. So okay, yeah. So let's say, so I presume n changes between 1, 2, 3, or pi, 2 pi, like that. Or what is n?
Oh, so this would be the mass of the particle, and this is its
No.
momentum.
No, I'm talking about n, like in
Oh, n?
Nevada.
Yeah. So n is just integers.
Okay, and n squared E1. So even if we have n equals 5, we have 5 squared multiplied in 1. Okay.
Yeah.
Thank you.
So the fifth eigenstate is the first eigenstate times 25. The sixth eigenstate is the first eigenstate times 36, and so forth.
Okay. Okay. Thank
All right.
you.
So now this brings us to the next thing, which is the let me do this again. So we have the energy of the system, and then if we were able to picture it, let's say that it was like, here are the energy levels, right? So here's energy level 1. And then the next one is higher than that one, and this is energy level 2. And then the next one is higher than that one, and this is energy level 3. And then the next one is way higher than that one, is over here. And they just keep going up. I mean, there's no limit to how many energy levels are. You can calculate them, right? And we just have that e to the n is equal to n squared h bar squared over 8ml squared. And that's the same as n squared e to the 1. All right, so this is what a boson would do. A boson is boring. A system comprised of boson is boring because their ground state is that all of the bosons like to be here. Bosons don't care that they're on top of each other. They can be on top of each other. They don't care about nothing. At absolute zero, they would all be there on top of each other, and they don't care. Questions about that?
You said boson, right?
Bosons, yeah.
Particles.
So particles that are bosons. So now we have that electrons are fermions. So let's say that we have a crystal. Number of electrons is given by, I don't know, some value c to the n, right? However many atoms you have in there is the n. However many particles of electrons are in there is given by the c per atom. And you have that many electrons on your system. Now, what the Pauli exclusion principle tells us is that these electrons are not gonna they're not gonna allow each other to be put in an energy level that is already with somebody. But it turns out that electrons also have a spin. So there's not just how much energy you have. So you have an electron, you also have that the electron can be a spin up and spin down. So in the first energy level, you will have the electron that is a spin up. And then there's another energy level, exactly the same one, that is for the electron that is a spin down. So now if you have another electron and you want to bring it in, it cannot go into E1 because the spin up position and the spin down position are already occupied. So the next one has to be here. And then you have another electron. If it's a spin down, then it would go here. And then the next electron that you see would go here. And then the next electron would go here and here. So in this case, if you have the crystal that we were thinking about, there are all of these energy levels given to you by the particle in the box of the system. And each of these energy level cannot support more than 2 electrons because it's the spin up electron and the spin down electron. And that's due to the Pauli principle. So no energy level can support more than 2 electrons in this one-dimensional, very simple kind of system that we're thinking about. The lowest energy configuration then, and that's the one that you will get at zero energy, at zero temperature, is this one, where the stacking of electrons goes like that. And now you have that there's this electron in E4 up here that is the highest energy, the electron with the higher energy. So if you start counting and stacking them up together, you can figure out how many energy levels you would need to have in your system occupied for all of the electrons to be positioned there. Okay?
So Dr. Miranda, the fact that so spin up is one quantum state, spin down is another quantum state.
Exactly.
And it's that differentiation that allows 2 electrons to occupy one energy level and still be in keeping with the Pauli exclusion principle, correct?
Exactly. That's why. That's the only reason that you can have 2.
Just wanted to make sure I was checking my understanding.
Yeah. So again, if you had bosons, you can put these 7 bosons. If you're looking for the ground state of the boson system, is when all 7 bosons are in the first eigenstate. But because you have electrons, if the electron system has 7 electrons, this many states have to be occupied. This is what the fermion rules are. And this is what the only thing that we have to worry about with the Pauli exclusion principle. So if we look at it, we can find out what is the energy. Well, the first thing is, what is the highest energy of the system? At this 0 temperature, and the highest energy occupied is given by, in this case, we call it the Fermi energy. That's what the little f is for. And we have the number of electrons that are in our system divided by 2, because there's 2 per energy level, squared times the first eigenstate of this box. This is the Fermi energy. Very important quantity. If you were in the colloquium right now, you saw something like called a band gap and so forth. The Fermi energy is right through the middle of the band gap that they were showing in the pictures. So it's something that you see all the time. Questions about this Fermi energy?
So what they call Fermi's velocity is the kinetic energy related to this, the velocity that corresponds to the kinetic energy related to this value. Okay.
That would give you the Fermi. So if you look at, we said that energy is equal to P squared over 2M, which is also 1/2 mv squared, right? So at the energy of Fermi energy, you can also write it as this. And that will give you the Fermi velocity. So the particle, in this case, the particle that is all the way up here, that one is the one that has the Fermi velocity of the system.
So in the Fermi energy formula, you have E1. So you're saying that the lowest energy, isn't it the highest energy level that's occupied by an electron? I think you mean E4, right? In the formula of...
In this case, it's E4, right? But E4, so we have 1, 2, 3, 4, 5, 6, 7. We will put 7 divided by 2 squared. It's close enough to E4.
No, I mean in this, I can't point, but in the formula you have EF equal to NE over 2 times E1. Shouldn't it be E4? Shouldn't it be the fourth level? The level that has the...
So yeah, that's a good point. So in this cartoon representation, this is the Fermi level.
Yeah, exactly. I think that's, you, instead of 4, you miss it.
What happened though is that this guy is 10 to the 23. Approximation of this being 10 to the 23 is not going to matter where the Fermi level is once you have enough numbers here.
Yeah.
You're right. When this very simple, just 7 electrons, then there's a little bit of discrepancy because the Fermi level is right here. I'll leave it there. Once you get into higher number, there's a lot of energy states, so you can be populated all the way.
Yeah. Oh, yeah. Also, the difference between these E4, E3 are very tiny compared to the 10 to the power 23. So yeah, it doesn't matter. But yeah, I just wanted to.
Yeah, and then once you're at this energies, well, sorry, now when NE is around 10 to the 23, then that means that we have a lot of electronic states there, right?
Yep.
E Fermi is that. And then for a metal, this Fermi velocity, which is given by this 1/2 mv squared, right? Energy is equal to 1/2 mv squared, and when you convert it, this gives you around 2 times 10 to the 6 meters per second, which is 1% of the speed of light. All right, so how fast are electrons traveling in a metal? Anybody knows?
I believe something like centimeter per second. Is that a good approximation?
Yep. Well, it depends on what metal, actually.
I think it was for a copper wire.
Okay, 10 to the 6 meters per second is the Fermi velocity. And it actually depends on what metal you're thinking about. But yeah, it's close to that value. All right, I see a question there, Zachary.
Yeah, so when talking about the Fermi energy in that equation that you have there, so there is no difference. So there is a difference in Fermi energy from 7 to 8 electrons. So I would think that the Fermi energy would always be the discrete energy E4, but if you have it at 7 or 8, the Fermi energy is not necessarily one of those discrete energies.
Right. When you have these very small numbers, then it doesn't match up with this formula. But once you have enough, it does match up.
Okay, I see. That was your explanation earlier. Okay.
Yeah. And in reality, what you would have is, once you have this many electrons, and we're going to get into this, you're going to have that this is the energy. And then you're going to have a bunch of energy states here that are filled, and then a bunch of energy states up here that are empty. And then your Fermi level is actually going to be somewhere in the middle. So at zero temperature, all of these black ones' energy levels are full. All of the orange ones are empty. And then your Fermi level is just half between the two. That's by definition where you find the Fermi level. Any other questions?
Yeah.
Yes.
Just a note. Oh, sorry, you go.
Yeah, yeah, continue. Sorry.
So looking at this formula where we get the Fermi velocity where it's it's 1% of the speed of light. So it seems to me that if we add enough electrons, we can kind of break the speed of light and go over it. Is that
actually, yeah.
we are not considering?
Yeah, so the issue is that you need to do, when we are doing classical mechanics, when we're doing quantum mechanics and when we're doing classical mechanics, we never take into account relativistic effects, right? So in this case,
okay, I see. Yeah.
that we're talking about are kind of like the modification to classical mechanics that takes you to that. If you were to deal with the relativistic quantum mechanics, which is the Dirac equation, then in that case, you have the corrections to this. So this classical mechanics of the particle in the box doesn't know about relativity.
Okay, so it works up to the number with respect to the speed of light is low enough.
Mm-hmm. Exactly.
Okay, thank you.
All right, I saw another question somewhere.
So my question is, yeah, might seem odd, but I was just wondering. So we are studying the energy band of the electrons. For example, you're doing now. So why do we need this? And also why we are concerned on the Fermi and the boson that it did the applications? Isn't it the high energy?
For the discussion of fermions and bosons is because bosons actually show up in condensed matter, solid state physics a lot for phonons. So I wanted to be sure whether you guys hear it a few times before we introduce phonons, right? Phonons are bosons. Electrons are fermions. And then the only thing that is important before getting to more complicated stuff is trying to get the very first simplest model to be able to introduce it and look at all of these important quantities that are going to get a little bit more complicated. So what we just did is the one-dimensional case, right? And if you open your book, we actually see that in page 17. Let's see, let me stop sharing and make sure that I can see the same as the book. So we went through this part that talks about dispersion relations. Sorry about that. So this we know. We also went through the second figure, which has the wave functions that you would be seeing, plus the energy levels.
Can you tell us the pages too, Dr. Bondon?
Yeah, page 18. And this is telling you how you have the same things that we were discussing. What are the energy levels? The example is the one that we have there. We have that because you have made it so that your box is finite. Now you have that the energy levels that are allowed are finite, right? And then they are in specific positions. The other thing that is important then is to look, and this is equation 2.8, is the same solutions, but now you're looking at a two-dimensional systems. And then if you continue seeing this, you're now going to a three-dimensional system. Okay? So the next thing that the book does is that it gives you, let's say now you're back in 3 dimensions. And you're seeing my screen again, hopefully. All right, you see my screen, right?
Yes.
Yes.
Awesome. So now, once we have that, we see that in 1D, we have this, no, sorry. So in 1D it was h bar squared k squared over 2m. This k is called the wave vector. And h bar k is equal to momentum, right? The other thing that we have then is that we know the energy levels. And if we go to 2 dimensions, we have h bar squared 2m, but now your momentum can be kx or ky. And because of the boundary conditions, this kx is, and also the ky is the analogous formulation, is nx pi over L, where nx is an integer that goes from 1 to all the way. Same thing for ny. And you would have the 2 there. And therefore, the energy in 2 dimensions is this h bar squared over 2m kx squared plus ky squared, which is the same. If we don't want to talk about it in wave vector, we can describe it in terms of these quantum numbers nx squared plus ny squared. Questions there? And then there's another one in 3D, which is the same thing. But now you have nx squared plus n sub y squared plus nc squared. Any questions so far?
I am so sorry again, but physically, what do they mean? 3D energy, 2D energy, and 1D energy? Is it something observable, or you're doing this in the sake of concept?
It's the energy of a one-dimensional system that is just a single particle in the box, or a quantum well, right? Like a single one-dimensional well, or a two-dimensional well, or a three-dimensional well. So in this approximation, this three-dimensional well is the crystal, right? If you have a crystal of sodium, of lithium, of whatever, then you can model it with this free electron gas, and this would be the energy levels. They have these quantum numbers nx, ny, and c. There's a volume attached to them, which is the cell cube. And then you have the mass of the electrons, and that's how you would describe it. And I don't know if that
2D and 1D? I say 2D and 1D hypothetical then.
So for instance, a two-dimensional one could be graphene. So graphene is a single layer material, right? So the behavior of graphene is not exactly like this, but it is a two-dimensional system.
So it doesn't count its width, even if it's small.
I'm sorry?
The graphene is a layer, but still it has some kind of width, isn't it?
Yeah, but it's a single atom with a couple of Armstrongs.
Also, our definition or dimensionality comes from the atom, right? One atom is 1D, I see.
Yeah, and if you had a one-dimensional one, it could be just a single chain of atoms, which is also possible.
Thank you.
All right. So what we have here, let's see, is that there's a relationship at this point that I want you to see. So we have a free Fermi gas, and we're assuming that the electrons don't interact with each other. We're also, or with the ions in the system, they're just inside the box, right? And we already know the solution to that. And that solution gives us these energy levels. But the reality is that we also have the solution with the plane waves. And I think we just discussed it barely, that there's plane wave solutions and there's your sines and cosines, but they're almost identical, right? So another way to solve it is to assume that you have the wave function is going to be represented by this wave vector of the system. So in that case, this guy in 3 dimensions is given by ny, nx, and nc. Can also be given by this guy. Now I'm just going to use the vector form of it. So this is the one that gets written with sine of constants times x, right? Sine of another constant times y, and so forth. And this one that I'm thinking about is the equivalent one. We have a normalization factor for it that is related to the volume of the system. This is a normalization function because our wave functions have to be normalized. And then it's an exponential, the imaginary number, the wave vector k dotted with the r position vector. R is this x, y, z vector. And what that tells us is that the wave vector can also be given by now I'm already using n's over here, right? So I don't want to use n's anymore. So let me use just little l because they're not the same number. And I'm doing that because Cherith or somebody else is going to tell me that that doesn't work because the boundary condition is not correct. Oh, Arman is going to tell me this.
Yeah, I was also gonna say that you have just a little typo in the E3D expression, but it's just you're using L cube, but it should be L square, right? In the expression of E3D.
This one is L squared. This one would be L cube. And the one dimensional should just have L. No?
Oh, okay. I'm thinking. Okay, you're thinking of. Yeah. So the n are different from the way I'm thinking. Okay. Yeah. I think
Right.
it works.
So that means that this L's and they're integers that go from negative infinity to infinity. Okay. And the reason for that is that this k is a vector, and this k is chosen so that this wave function right here satisfy the simple Hamiltonian that we had before. And only if you do it, you cannot do it from 1 to infinity, you have to do it from negative infinity to infinity for it to work. Okay? Questions? Anybody? Armand, you have a question? No? I see your hand up.
That was from before. I'm sorry. There's probably a way.
Anybody has a question? No? All right, so then let's recap what we were saying. If we want to figure out what the ground state is for n electrons, what you want to do is that you start by putting 2 electrons into the single particle state with the lowest energy. So if we look at this, guys, the lowest energy state would be, oops. So we're going to put n electrons, right? How do we, the ground state that we want to build is such that we start by putting, out of those n electrons, we put 2 electrons into the first single particle state, the one that has the lowest energy. So the one that has the lowest energy is going to be, and it would be this one that has energy where this is 1, 1, and 1, right? So we have 1 square plus 1 square plus 1 square. And then it has whatever value of energy it is in this 3D crystal. But this one goes from infinity to infinity. So we're going to find the lowest energy eigenstate is the one that corresponds to K.
Dr. Brenda, you're, I don't know if it's just mine, but the n electrons with the arrow next to it at the bottom of the page is cut in half. I don't know if you need to scroll down or scroll up. Or,
oh, okay.
I think you're outside of the window. I can't see anything below that.
All right, so let me start a new page.
Thanks.
Where was I? So we have, let me write the K again. My K is given by 2 pi over L. And then some quantity Lx, Ly, and Lc, where L goes from, has a range, are integers between negative infinity and infinity. So then the first, we want to put n electrons. Where do they go?
In the lowest energy configuration, or in the lowest level, right?
2 go into the lowest energy. So you're putting 2 in a state that has this. So this K is a vector, but we can find a magnitude of K2. And the first one, the lowest occupied one, is the one that is the smallest one, right? Is K is equal to 0. And then I put 2 there. So then you're going to put electrons 2 at a time into this state, into a state. So I'm trying to erase here. Somehow, sometimes it erases, sometimes it's not. I think it's because I chose the wrong pencil over here. So I cannot erase ink or something silly like that. Anyways, so now we have the next one.
Do you have maybe a button on the pen? Yeah, just because I have a Surface and sometimes I press the button without realizing it and it erases. Maybe it's similar for you.
Maybe. I haven't learned how to use this. But then we're going to put 2 whenever this K vector, the magnitude of it, is 2 pi over L. So that would be that either this one, Lx, Ly, or Lc are there. So that means that we actually can put 2 go into K being 2 pi over L in the X direction, right? No, sorry. Nah, maybe this is confusing. But yeah, K is going to be Kx, which is just 2 pi over L, or Ky, or Kc. So I have the first two go here. Then I have not just two, I can put two here. I can put two here, and I can put another two here. And then I can keep going on that because I have 2 pi over L distance. So here, this is the picture that you see in the book in figure 2.3, page 20. And let me do a very simple approach, which is I'm not going to draw the KC axis coming out. So this is the KX axis. This is the KY axis. There's also the KC axis, but I'm not going to show it there. So I'm going to have that there's 2 electrons here in green. Okay. Then there's 2 electrons here. And then there's 2 electrons here. Now, I also can do it. So I want it in all the places where the K vector is 2 pi over L. So actually, I can put another 2 here. So you know what? Let me do another color. So the green one is for the 0 ones. This is the lowest energy. That's that one. Then I can use another color. This is for all of these values. So I can put 2 here. I can put 2 here, right? So that would be Kx, Ky, negative Kx, negative Ky. I could actually put the ones on the Kc axis, but I'm not drawing that one because that would get blocked. So that means that I'm able to put not just 2 in 2 pi L when the magnitude of K is 2 pi L, but I can put it on all those points of where the magnitude of K reaches that value. Does that make sense? Yes, no?
Is K, can it be negative for the, is this the periodic boundary conditions or is this the box boundary conditions?
So in this case is the box, but the way that we define K with the wave vector, the boundary conditions are such that L can go negative or positive, and even 0.
Okay.
So it's not the same as the number L. So actually we have this one, right? This one too. And this one too. So that means that I was able to put 2 in the lowest eigenstate and that I have 12 electrons around it in the next occupied state. So that means there's a degeneracy of the second eigenstate, because it could be with this K, or 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 this K. All those possible Ks. And then I also have another one, right? Because there's a K over here, and I could put it there, 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 there. And it's all of these different states are being occupied. I can start putting electrons all the way to up to whenever it's occupied. And what happens is that you're building up this thing. When you have enough electrons, you're gonna get maybe something that when you have n to the 20 something electrons, right? Maybe you're gonna get something that looks like almost like a sphere. It's not really a sphere because if you were to zoom in, right? If you were to zoom in really low, really in, you would see that grid of electrons being occupied like that. If you were to zoom in all the way in. But once you have high end, right? high number of electrons there.
So the orange line will correspond. Yeah, I guess that you already marked the same K value modulus, like its
right.
size.
Exactly, and all of those guys are occupied up to there. And with that, I could say that this vector from here to here is my Fermi wave vector, Kf. So this is not a, no, sorry, it's the magnitude of that wave vector, right? It's not a vector, it's just the magnitude. And it's that this Kf creates a sphere. It gives you a sphere in 3D. All of the electrons that are occupied are inside of the sphere. All of the energy levels that are unoccupied are outside of the sphere. If you're in a two-dimensional system, it will give you this circle, right? But the main thing is that this thing is what we call the Fermi sphere. So you have a ground state of all of these electron states being occupied with n electrons. You start filling up this collection of energy states that are given in K space, in wave vector space, and you fill it up, you're gonna fill up a cubic grid of states that as you start looking at them, it starts looking like a sphere. You're putting, if you put any other shape in there, you would have that there's a space missing, right? You want to pack them as close to the origin because those are the first those are the first states that get packed in, that get occupied. And then you start filling them up as you go above on a higher and higher energy. And you want to minimize the energy, you end up with the sphere looking thing that is full of electrons in the inside. All right, go ahead, ask your question.
So I was thinking that just like we can associate a Fermi velocity with the Fermi energy with E equal to half mv square. So for this Fermi vector, maybe we can do the same. Like it should correspond with the Fermi energy through the relation of E equal to h squared square k square over 2m. Does that correspond to the Fermi energy?
And that's our Fermi velocity and our Fermi wave vector are very related, right?
So yeah, both of them would correspond to the corresponding Fermi energy through these equations. Okay.
And yeah, exactly. And then there's a relationship that you're seeing already. The Fermi energy gives you how many electrons you have on your system, which gives you basically the density of electrons that you have on your system. It gives you how fast, because it gives you a Fermi velocity, is the most energetic electron moving on. And it gives you what kind of wave vector. And this wave vector is related to the wavelength of the system too, right? So it gives you what, so just to, this guy is proportional to this wavelength that we were thinking about. Okay? So if you have the lowest approximation that we can think about, which is this Fermi free electron gas, there's no interaction with the electrons. We just took into account that there's a Pauli exclusion principle that doesn't let the electrons be all occupying the same ground state level, that you can only put 2 per state. You end up with a Fermi sphere that tells you which ones are the states that are occupied and which ones are not. How does that make sense to all of you at this point? And how we put it together, that there's no other shape that would be better at packing all of this in this thing that is called K-space. K-space, because it's not really X and Y, it's more like wave vector in the x direction, wave vector in the y direction, right? So let's call it k-space. So
yeah, this
no.
this makes sense. I just wanted to sort of clarify that the Fermi velocity we have, that's, I mean, it's obviously not a physical thing, but it's also not a physical measure of the actual speed of the electrons, right? Because obviously the electrons on each individual electrons are not moving that fast. I just wanted to like make sure that it's
exactly. It's not.
It's not a physical thing. It gives a good idea of the physical thing, but the values themselves are not physical values at all. Actually, very
actually,
far.
they are.
They're like the real physical values.
They're very close to them, except that this is a very brute, rough approximation. But basically, what we're saying is that this electron right here, the one in the center, is not moving, right? It's the one with the lowest speed. And then this one, and this one, and this one, this one, and this one have the same speed.
Yes, it gives us that idea, that which is the physical truth, but the values we get from Fermi velocity are very high, like in the scale of 10 to the power 6. But physical real electrons, they might rotate at that speed, but they don't have the translational velocity of that high speed, do they?
Oh, so I have a homework for that you get to do.
Okay, nice.
Compare those values to the experimental values. But we'll get to that later, okay?
I guess I'll get my answer in that homework then, okay.
All right. So I think it's time, this is where I wanted to stop, and I think is over time by a little bit. So I don't know if you guys have questions. If not, this is where I want to stop.
Just a quick question, just to see if I understand. So we cannot have at least a 0 Kelvin any electron above the maximum state that this Fermi rule defines. So if I have two crystals at 0 Kelvin, two sodium crystals, and they have a bunch of electrons at their perfect minimum state, and they fill all the energy levels up to the Fermi level, and I all of a sudden put them in contact. Do the electrons reorganize and go to fill all the Fermi? They get to a new Fermi level?
Right, they would reorganize, and if they were different densities of electrons in each of the two materials, then they would come to the middle in between the two, right? So you will have a different, but yeah, I think that's exactly what would happen. You will have, if you have different densities on the materials, if they're the same density of electrons in the materials and you put them together, it's like you just double the size of it, but double everything the same. But if one has this particular density and the other one has another particular density, then they would take a little bit of time. It wouldn't be instantaneous, but they would homogenize and have the same everything across them.
It's like when you have like two glasses of water of different height and somehow you merge them, then it gets to the minimum height, minimum combined height. It's like two glasses of water, because everything wants to be in a minimum potential. It could be the minimum ground level of electron or the height of the water level. It's all about minimum potential, right?
Yeah.
Okay, thank you.
All right, so I'll see you guys on Tuesday. And it looks like the cases are going down all over the country. So hopefully nothing bad happens from here to then. You all have fun, and we'll be in person for the next class, okay?
Thank you.
See you, everybody.
Have a nice weekend.
Thanks so much. Have a good day. Have a good night.